Okay, so picking back up at where we are here, we now have 3 points that we can kind of figure out what this sideways parabola, half a parabola, whatever you want to call it, is going to look like. So when we go 3, we're going to get 3 here. And when we plug in 27, we're going to get 9, which is out here. And so what you'll see is that that 3 inside actually stretched that parabola up, just like a 3 in front of pretty much any polynomial is going to stretch it. Now, if we look at B, and we're going to look at the parent function. I'm going to draw a line here for you guys. Hopefully you have enough room to take notes in your books. But with this one, if we look at the cube root function again, so y equals our parent function, which is the cube root of x. In this case, we want our x's, again, to be the perfect cubes, so that when we plug them in, we're getting nice, pretty numbers out for y. So we know that -8 is a perfect cube, and the cube root of that is -2, -1 and -1, 0 and 0, and finally 1, 1, 2, and 8. So, ooh, did that backwards. Hope you all caught that. 8 and 2. So it's going to look something like this. So that, again, looks like a cube function, just rotated. So now let's talk about what this is going to look like. So when we picked our x's above, we picked squares. But since our index here is a cube, we need to make sure that our x's are going to give us perfect cubes underneath that cube root sign, that radical. So we've got 1, 2. We're going to need to multiply it by 2 more 2's, which means that this is our first x we're going to use. When we plug that in, we get the cube root of 8, which is 2. Actually, we're going to do this in blue on the graph. So I'm going to throw that up there. So we plug in 4, we get 2. Now, I need another triple of 2's, right? So we've got 2 times 2 times 2 times 2 times 2 times 2. So this is our 2 that's originally in the problem. Here are all the 2's we're adding. So that means that x is 2 to the 5th, which is 32, but that our y is then going to be 4. And if we decided that x was -4, our y is going to be -2. And if our x is -32, then our y is -4. And of course, 0 and 0 should all be on there. So 4 and 2. 32 is not anywhere on our thing. We're just going to assume that it's way over here, but it's at 4. And then we're going to have 0, 0, -4, -2, and 32, 4, way, way out there somewhere. So when we graph that, we see that that 2 inside again stretched our parent function up and down. So when we go on to example 2, the nice thing is you guys have there in the top of your notes how these shifts happen to that parent function. So of course, in this case, your h is underneath the radical. Your k is out here, hanging out outside the radical. And then your a, which is out front, gives you a vertical stretch or compression, just like it does when we're talking about all of our other parent functions. So now, when we're talking about domain and range for this, our range, let me erase here. We didn't talk about range in example 1. We should go back. Sorry. We talked about our domain being 0 to infinity. Our range on this parent function is also 0 to infinity, because when we plug in the minimum for our domain, we get the minimum for our range. And it's the same kind of concept with this. You'll notice that for this function, though, our domain is negative infinity to positive infinity, and our range is also negative infinity to positive infinity. When you have an odd powered index, this is something you're going to want to write down. An odd powered index, probably odd index, your domain is negative infinity to positive infinity, and your range is negative infinity to positive infinity. But when you have an even index, your domain and range are determined by what's under the radicand. So you're going to determine by setting the radicand equal to 0 and solving. This gives you your min for your domain. And then when you plug in the min for the domain, you get the min for the range. So now let's talk about example 2. Okay, so up at the top, you guys have your A, H, and X. So to find our domain first, we're going to take what's under right there, the X plus 3, and we're going to say that that has to be greater than or equal to 0, which means that X has to be greater than or equal to negative 3. Then for our range, so that's our domain, it's going to be negative 3 to infinity. And for our range, we're going to plug in that negative 3 and see what pops out. So we're going to have g of x equals 2 times the square root of negative 3 plus 3 plus 5. So 2, negative 3 plus 3 is 0 plus 5. 2 times 0 is just 0 plus 5. So 5 is the minimum for our range. So there's our domain and range. Now comes the really hard part. We've got to figure out how to pick x's so that we're getting nice, pretty numbers there for our domain and range. Or you can just remember what's happening with your parent function. So we're going to start over here at negative 3, 5. That's going to be our new vertex. And I love how they gave us a graph with even spacing, and we're starting out with an odd shift. Gotta love Pearson for that reason. And then recall that typically that in the parent function, you would go up 1 over 1 because you've got that 1, 1 as your next x and y. Well, that 2 out in front says, nope, we're not going over 1, up 1. We're going to go over 1 and up 2. Because we're taking that value and multiplying it by 2. So we're going to go over 1 and up 2. And that will give us our next value. which is going to be